Hi everyone, Mrs. Basega here, and today we're looking at the midterm review. In this case, there are actually three different formatives that I'm going to go through in this video. So as we go through, I'm going to try and identify which unit is something from and what are the main concepts from that unit. So let's get this started. In midterm practice 1, we have two repelling pith balls. These are spheres covered in conductive coatings that make them easy to hold charge. So in this case, a sphere is charged with 3 microcoulombs. That's 3 times 10 to the negative 6 coulombs of charge. And because it's positive, that means there are more protons than electrons on the sphere. This concept is from Unit 6. In Unit 6, we dealt with the idea of charge and net charge. Be able to figure out the charge or net charge on an object and relate that back to the types of particles in atoms, like protons, neutrons, and electrons. Number 2, calculate the weight of the sphere. We know the sphere has a mass of 50 grams. And this is a question all the way from Unit 1. We originally did this problem in August. Calculating weight is Fg equals mg. The mass is 50 grams, but that's 0.05 kilograms. The field of Earth, it's 9.8 newtons per kilogram. And think about what that means. It means that every 1 kilogram of mass has a weight of 9.8 newtons. So in this case, if I have a fraction of a kilogram, I should have a fraction of 9.8, and I multiply this out. This gets us 0.49 newtons. You get 1 point for the equation, 1 point for substitution, 1 point for the solution, but in this case, because there was this conversion factor of you had to change grams to kilograms, you get a point for the conversion too. In this case, it is 0.05 kilograms because we took 50 grams and divided by 1,000 to get kilograms. Now, electric force has two different equations. I could do either Coulomb's law equation, this Fe equals kq1q2 over r squared, or the electric field equation. It doesn't make sense to do the field one because we know the two spheres' charges. So I've got my equation, I substitute k. I'm substituting in 3 microcoulombs, and I would get that extra point there because there's the conversion factor to micro. And they are 1 meter apart. So when I'm doing this 1 over r squared, that's 1 squared in the denominator. This ends up being 0.081 newtons. And this was a Unit 6 concept, be able to calculate electric force between two spheres. Specifically, because this force looks like the gravitational force, be able to compare and contrast electricity and gravity. You'll notice all of these practice problems have free body diagrams. And that's because that's a central concept to this course. So a free body diagram should have forces pointed away from a central dot. They should be drawn proportionally. In this case, you just calculated out the electric force, but it's hard to draw it proportionally just because the electric force was so much smaller than the gravity force. You know what I'm doing here, though. The longer the arrow, the stronger the force. These vectors point away from the central dot, and I know this is an equilibrium, so there's got to be a tension force up here. This follows the string, pulling up and to the right. You don't need to draw the forces on sphere B. A free body diagram just deals with the forces on one object. So all the way from Unit 1, be able to draw a free body diagram. Question 5 is from Unit 1 as well. Which force acting on sphere A has the largest magnitude? If I look back at my free body diagram, I see that this should be an equilibrium. That means that the tension force has to balance Fg going down with its own y component going up. It's supposed to be balanced, but it's not perfect. Balancing the x component going right with Fe going left. Because tension has to cancel two forces, not just one force, tension has to be the biggest force. Because the object is in equilibrium, the net force has to be zero. The forces must be balanced. That's all from Unit 1. Because the forces are balanced, that means the net force is zero. The force going to the right should cancel the force going to the left. Because the forces cancel, there's no net or extra force left over. Be able to calculate the net force for balanced things having zero net force, and unbalanced things are going to have the net force causing mass to accelerate. Now we move up to Unit 5. Do expect that the midterm will jump around from unit to unit. In Unit 5, we were doing how potential energy changes to kinetic energy. So when the ball is at the top of its motion, it has PEG. All of the PEG turns to KE as it falls. The direction doesn't matter because energy is a scalar. So the fact that it's like falling and being repelled away from the other sphere is not a big deal. It's still going to start above the ground and speed up. This is a ball that's falling, so the ball has the kinetic energy and the Earth has the gravitational potential energy. Be able to draw energy bar charts, identify objects in the system, calculate speeds and kinetic energies, all of that from Unit 5. Then we rewind backwards. Sphere A has this impact with the ground and it bounces. A force pair is a pair of forces that interact via Newton's third law. It always has to have the same two objects. So in this case, this is sphere A in the air, sphere A in the earth, sphere A in the floor, and all three of these choices do a good job of staying consistent. They all have only two objects. If it had a third object, you could automatically cross that out. Forces are an interaction between two objects. So let's see if the directions make sense. These need to be equal in magnitude and opposite in direction. So they can't both pull up, and they can't both pull down. Let's read through this one. So sphere A pushes the floor down, and the floor pushes A up via the normal force. That must be it. Be able to identify force pairs in the system. Force pairs are interactions between two objects. Forces are going to be equal in magnitude and opposite in direction. Continuing along with Unit 4 with momentum. Momentum is changed in this picture. It's both changed its magnitude, that is its absolute value. So think the momentum is mass times velocity. So it starts with a negative momentum and it ends with a positive momentum that is smaller. So the magnitude of momentum is decreased, and so it can't be this one because magnitude of momentum is decreased, and the direction changes because before it was going down, now it's going up, and momentum is a vector. All right, on to midterm practice 2. We were looking at a pendulum that swings back and forth. If you didn't get a chance to before, actually watch this whole video. It's great because it shows how long of a string 67 meters is. You can see that it's hung from one of these old school European buildings, going all the way to the top of this dome here. So cool. But like I said, be able to draw free body diagrams. In this case, dot starts in the middle, FG goes down, FT goes up and to the right. You get a point for the structure, so it has to have vectors pointing away from the dot, a point for identifying the forces in the picture, and a point for their direction. Hey, calculating weight again. Weight is caused by the gravitational field of the Earth acting on a mass. The mass is 28 kilograms. The Earth's field is 9.8 newtons per kilogram. So the gravitational force is going to be 274 newtons down. The length in this problem is extra information that you do not need in order to solve it. In problem 3, we've got a problem from unit 3. So this is an object in circular motion. Because it's in circular motion, there must be a net centripetal force acting towards the center of the circle. So not the center of like this sphere, not like this circle. Undo. This circle, the axis. Centripetal means center seeking, so there should be a force pointed towards the center of the circle. You can kind of think of it as like the inertia, the tangential velocity of this sphere is to the right. That's the direction it would go if there was no centripetal force. But because the centripetal force is pulling up, the sphere starts to move up. And that changing direction is caused by a centripetal acceleration. So the centripetal force and then centripetal acceleration are center seeking, pointing towards the center of the circle. And if those forces and accelerations weren't there, then this object would go along its tangential path in a straight line forever and ever and ever. Done. Even though this is a circular motion picture, this is not a circular motion question for problem number 4. This is a way back in Unit 1 question. In this problem, the sphere has a weight of 274 newtons and experiences a tension of 350 newtons up. Someone was asking me, like, is there an equation for net force? There's not an equation for net force on your equation sheet, but rather this idea that net force is how much cancels out. So if there's a force up and a force down, they work against each other. Remember, in this case, there was this sphere, and the sphere had a force of tension pulling up and gravity pulling down. These two partially cancel each other out. Tension is the force that pulls up at 350 newtons. Gravity was the force that pulls down at 274 newtons, leaving 76 newtons left over. That 76 newtons actually, it acts towards the center of the circle and makes this object move in a circle. The 76 newtons is the centripetal force that's trying to make this thing change direction and move upward. In number 5, there are a lot of ways to calculate acceleration. If it's in free fall, the acceleration is 9.8. If it is going downhill, the acceleration depends on the components of gravity. Let's just look at the two most fundamental ways to calculate acceleration. We've got the definition of acceleration, where acceleration causes a change in a velocity to occur over time, and Newton's second law, the net forces cause mass to accelerate. But look at this information you have here, guys. We don't know the velocities, but we do know the net force. So A is equal to that 76 newtons net force that didn't cancel out, acting on 28 kilograms of mass. Dividing that out gets us 2.71 meters per second squared. The reason this makes sense to me is it can't be that close to 9.8. So this answer, not going to cut it. It certainly can't be faster than 9.8 because tension is slowing it down, right? Like tension and gravity are acting against each other, so it can't be faster than 9.8. That doesn't make sense. So between the two choices, I just had to make sure I did my math really carefully. Equilibrium means that forces are balanced. This was the fundamental idea of Unit 1, was that when forces are balanced, the net force is 0, and therefore objects in motion stay in motion. But guys, this is not just like, motion however it's moving. It's motion in a straight line at a constant velocity, and that's not what's going on. So obviously the pendulum is not static. It's swinging back and forth, and it's not dynamic equilibrium because while it is moving, it's changing direction and it speeds up and slows down throughout the course of its motion. It is not in equilibrium because the forces are unbalanced. This is accelerating because it speeds up and slows down as it moves. Now, we talked about force pairs already. Force pairs are when you have a pair of objects that interact with each other. So you actually have a lot of choices here. Just to give you an idea, you could say that the Bob pulls Earth up and Earth pulls Bob down. That would be the gravity force. Okay. You could do something like the string pulls the Bob up and the Bob pulls the string down. That would work. You could even do the air resistance force. So maybe something like the ball pulls the air right and the air pulls the ball left through drag. But things you should make sure you're doing is when you are identifying a force pair, pick your two objects, so Bob and the Earth. That's one pair. One pulls down, one pulls up. Check. And then see if you can, just for funsies, think of what force that is. So gravity is the force between the Bob, that's the ball at the end of this pendulum here, and the Earth. Number 8 is a tricky question. We haven't done a lot of speed versus time graphs. And in this one, this is an object that starts at rest at A and then speeds up at B. So it can't be this picture because that shows an object in constant velocity. It can't be this picture because that's something that's slowing down. When I'm choosing between this graph that curves down and the graph that curves up, that's actually kind of tricky. I'm picking the graph that curves down. And if you have trouble figuring out why off the top of your head, you can kind of picture this as our skateboarder is falling from the side, that would be the equivalent of point A, to the center. Look at this kinetic energy graph. The kinetic energy starts small and increases to a maximum with that downward facing curve. Honestly, I didn't expect that question to be as hard as I wrote it. Um, I was picturing that like you would select the one that shows speeding up, but then I put two that were speeding up. So sorry about that. This answer is B. It's showing speeding up as it's approaching the center. That rate of change gets slower. As long as you can identify speeding up and slowing down from a velocity versus time graph, you're pretty good. So what about energy bar chart? In this case, this starts as potential energy and goes to kinetic. In this case, I did not put down the labels for the columns, so you need to put those down so I can see that you understand which two energies it's going between. So the pendulum bob has the kinetic energy, the Earth has the gravitational potential energy. They transfer energy back and forth between each other, so the energy before equals energy after. So this is that problem I mentioned earlier. Be able to calculate energies. While it says total mechanical energy, that really means I have two choices. I can either calculate PEG at point A or KE at point B. And I have enough information for one of those, but not the other. I don't know anything about speeds at this point, so I can't use kinetic energy. The mechanical energy of the system is PEG plus KE plus spring, but there is only PEG at point A, so this is actually sufficient. This is a 28 kilogram sphere in a field of 9.8, 2 meters above the ground. This gets us 548.8 joules, which I'm going to round to 549. That total mechanical energy in the system is the energy both before and after. In fact, going back to my beautiful bar chart over here, if there's 549 at the beginning, there's 549 at the end, and these are our mechanical energies. With spring in here, but the spring was 0, so oh well. If the energy before is equal to the energy after, I can use the kinetic energy to calculate the speed. I didn't leave myself room to do so, so I'm going to fix that by the time it's your turn to do this. I'll actually just solve it up here. If I know the kinetic energy is 549 and the mass is 28 kilograms, I can solve for speed. First, I'm going to multiply 1/2 by 28. This gets us 14. I'm going to divide by 14 on both sides to get 39, then square root left and right to get the speed of 6.24 meters per second. So carrying that over to the problem I'm actually doing, that would be here, 6.24, which brings us to our final one. In this problem, we're talking about capacitors, but we're going to start all the way back at the model of the atom, because this is something you should still be able to do. So I want to draw some protons and neutrons inside my nucleus. Inside the nucleus, protons and neutrons are bonded together by the strong nuclear force. That leaves all the electrons on the outside of the nucleus, inside what's called the electron cloud. I'm trying to draw these electrons as random throughout here. I don't want to see orbitals. I don't want to see an electron dot diagram. While they're all models and representations of the atom, the reason physicists like this one is because it's as close to the modern understanding of the atom as possible. The electrons exist in the electron cloud, and because some of them are on average farther away from the center, those are the valence electrons and are easier to bond than maybe ones that are really close to the surface of the nucleus. And number two, we're doing another problem from Unit 6, electrostatics, and it's looking for the attractive force between the electron and proton. I'm using Coulomb's law for this one because I don't have an electric field, so I have to use K and the two charges. K is 9 times 10 to the ninth, and each of the protons and the electrons have the same magnitude charge. Like, yeah, the electron has a negative sign up front, but what's that matter if you absolute value this? Divided by r squared, so that's 5.29 times 10 to the negative 11th, all squared. I know some people are hesitant about using Desmos, but let me show you why I like Desmos. So I'm going to start with my numbers, my 9 times 10 to the ninth in the numerator. I like this gives me a running number as I go. So as it's evaluating, you can see my progress. I also like that it lets me see if I've messed up anywhere. So this is my value for Q1. This is my value for Q2. And I can see that I'm doing everything with the right order of operations. Okay, so let's say I get to the end. I've typed in all my things, and oh my gosh, I realized I messed up a number. I forgot a square on the bottom term. Well, one nice thing about Desmos is you don't have to retype everything. You can just go back in and edit. You can even copy paste. So if you were like writing it out in a lab on one page in a Google Doc, you could copy that number and it would evaluate it in Desmos for you. So this force is 8.2 times 10 to the negative 8th newtons. In my head, this number makes sense because it's showing me that the force is not too small, like 10 to the negative 18th newtons is too small. The electric force is very big compared to the gravity force. But it's also still on microscopic scale, so it should not be a large number of newtons here. Now, comparatively, the electron and proton both experience the same force. This is a Newton's third law force pair. So the electron pulls the proton right, the proton pulls the electron left. They have equal magnitude forces. But one might move faster than the other if one is lighter than the other. Like I said before, be able to tell apart gravity and electricity. Be able to describe both things they have in common and things that are different between each other. Things they have in common include the fact that they're both inverse square laws, not just straight inverses, inverse square laws. These forces both have are results of fields that spread out equally in all directions. And because that shape that it spreads out over is a sphere, well, the farther away you get from the source, the more that field is spread out, the weaker the force for both gravity and electricity. So they have in common this inverse square law. They have in common that they're both field forces. They have in common that they apply action at a distance. They both depend on universal constants. They're also dissimilar to each other, too. Gravity just deals with mass, while electricity deals with charge. Electricity is stronger, gravity is weaker. Be able to write about that. Now, if a proton and electron are kind of like in orbit here, that means there must be some sort of centripetal force. Now, in real life, this is not a perfect circle. I mentioned that earlier. But on average, there is a centripetal force holding the electron in towards the center of this circle. That's why, on average, this is like a cloud that is spherical in shape. Centripetal force causes centripetal acceleration. Centripetal acceleration is what's making the electron change direction. You can think of it as the electron would have gone in a straight line, off on a tangent, forever and ever, except that the centripetal force is pulling it right, so it turns right. As the electron orbits the proton, its momentum stays the same magnitude, so it can't be this choice. It stays the same magnitude, so it can't be this choice. Think on average, as it's going around, sometimes it's going left, sometimes it's going up, sometimes it's going down, but on average, that speed is staying the same. So the magnitude of momentum stays the same. Momentum is mass times velocity. So if the speed isn't changing, the momentum stays the same, at least the same magnitude, but the direction changes as it goes in a circle. Sometimes it's going left and sometimes it's going right. So the momentum changes from positive to negative as it goes. For number 7, the top plate of a capacitor is negatively charged. So the top plate has more electrons than it does protons. Once the capacitor is charged, it's going to close the switch and watch these electrons flow from the negative to the positive. It's going to do it again in a sec. So all this electrical potential energy in the capacitor starts flowing through the wire, through the light bulb, back to the positive side of the capacitor. So electric potential energy is creating light. Be able to identify the different types of energy. So this is electricity in the capacitor turning to light in the light bulb. Okay, now power is the rate that work is done over time. Alternatively, you could say something like power is the rate that energy changes, right? Because work is the change in energy of a system. These two statements are equivalent. So if the light bulb is emitting 0.33 joules of energy in 4 seconds, that gives a power of 0.083 watts. A watt is how many joules get transformed every second. And in this case, this is transforming from electrical to radiant, and probably a little bit of heat too. And finally, which of the following graphs shows how the drift velocity changes during the 4 seconds of time? Look on the side. The velocity starts at 12 centimeters per second and slows down to 0. I know these are really tiny to see. We'll fix that a little bit later. So the velocity doesn't stay constant. It's not number 1. The velocity does decrease, so 2 is a possibility. C shows the velocity speeding up. That's not possible. And 4, it shows speeding up, so the velocity starts low and ends high. Even though it has that downward facing curve, this would still be speeding up, so still not that. It must be number 2. All right, everyone, so best of luck on your midterm. You've got some things to study for. Be well.